All right, so sometimes instead of working with the entire vector space, we only need to have some subset of the vector space. But we still want to have all those nice properties we get from having a vector space. So we're going to let V be a vector space. If W is a subset of V, this is going to be a subspace if it satisfies the following three properties. So we don't need all the properties we had from before for vector spaces. We only need three if it's a subspace. So first, the zero vector is an element of W. So we don't allow our W to be empty, and so we're going to require that it has the zero vector. We're going to let U be in W and alpha be a scalar. Then alpha U is in W. So it has the closed under multiplication. And we're going to let U and V be in W. And then U plus V has to also be in W. So in other words, it's closed under vector addition. So these are the only three things we need to show that V is a subspace. Note that if we really wanted to, we could combine conditions 2 and 3 at once to say that we're closed under linear combinations. And then all we would need is the zero vector. And we would need, for if we had U and V and alpha 1 and alpha 2, we would need alpha U plus beta V to be part of our potential subspace W. So the reason that these are the only two properties that are necessary is if we're a subspace, if W is a subspace of V, then we get the vector properties. So those ones that we don't normally check are the things that we just kind of immediately get. The scalar one still exists, which is nice. And we already have the zero vector, which is nice. So we just need to make sure we have the closure properties as well. So if we get those three things from above, the rest we inherit by being a subset of the vector space. So if we want to go ahead and show that we're a subspace, there's two ways to do it. The way that we described last video with our spanning set stuff is that if we can take our set and write it as the span of some vectors, then it's a vector space and a subspace as well. Other way is we can check these three conditions that we talked about above and kind of pick arbitrary vectors U and V and an arbitrary scalar alpha in order to help us get there. Now, this first method is more important if you're trying to show that something isn't a subspace and that it breaks. Because if you can't write it as a span, you need to show which of these things is going to break down. So let's look at an example. Let's say we wanted to look at the set W, which is the set of all x, y, and R2, such that negative 2x plus 7y equals 9, and x minus 4y equaled negative 2. We want to know if it's a subspace. So we want to first know, we'd go through all of our properties. The first property is the zero vector, which in this case is 0, 0, an element of W? And, well, let's just look at our conditions here. 2 times 0, negative 2 times 0 plus 7 times 0 is equal to 0, which is not 9. So, no, W is not a subspace. It fails the first property. Fails one of our properties. So note that a line in R2 that doesn't go through the origin isn't a subspace of R2, nor does a hyperplane in Rn that doesn't contain the zero vector ends up being a subspace either. So let's say we wanted to go ahead and look at R2 compared to R3 and see if R2 was a subspace of R3. Well, no, because R2 is not a subset of R3. So notice that R2 are things that look like X, Y, and that is not a subset of things that look like X, Y, Z. So what we're saying is that they need to have kind of the same number of elements, and then from there we need to have, in order for it to be a subset, kind of some more restrictions on those elements. So let's say we wanted to go ahead and check if this set W, which was the set of all A times 2, 1, such that A is a real number, is a subspace of R2. So we're going to check some things. We'll do this both ways. So first we want to know if the 0 vector is in there. So 0, 0, which is just 0 times 2, 1, is in W. First property is good. Then we'd want to check if alpha times u1, u2, for some u1, u2 in here, was going to work. And so this would be alpha times A times 2, 1. So A times 2, 1 we're going to use as our arbitrary representative. And so we get alpha A times 2, 1 is an element of W. So that's in there because it is some number times 2, 1. That's what makes it part of W. And then last but not least, we want to know if I take some A times 2, 1 plus some B times 2, 1, so both of these individually are in W, we get A plus B times 2, 1, and so we have some number times the vector 2, 1, so this is in W. And so because of these three things, yes, W is a subspace of R2. So that's the hard way. The easy way is to recognize that W equals set of all A times 2, 1, such that A is an element of the real numbers. And this is our definition for the span of 2, 1. So there's an easier way of doing that, and that's just showing that it was the span. So let's go ahead and look at one more example. Let's say we wanted to let V be the set of all x, y, z in R3, such that x plus y plus z equals 0 and 3x plus 3y plus 3z equals 0. We want to write V as a span to show that it's a subspace. So first we need to take our constraints and solve for what the solutions are going to be. So x plus y plus z equals 0. 3x plus 3y plus 3z equals 0. And so here we'll get 1, 1, 1, 0, and then we'll get 3, 3, 3, 0. In order to row reduce this, we'll take row 2 and set it equal to row 2 minus 3 row 1. And we'll end up getting 1, 1, 1, 0, 0, 0, 0, 0. And so here, notice we have two columns that do not have leading terms. And so both y and z are free variables. And so taking this into account, V is our set from before of x, y, z, such that x plus y plus z equals 0. We can rewrite that to be the set of x, y, z, such that x equals negative y minus z. And if we take that restriction and put it in, what we'll get is negative y minus z, y, z, such that y and z are real numbers, is now how we can write our set. So notice that we took our restriction, we put it into our vector form, and now we have no other restrictions, so our y's and our z's are going to just be anything in the real numbers. This can be rewritten to break it down into a y part and a z part. So we've got y times negative 1, 1, 0 plus z times negative 1, 0, 1, such that y and z are in the real numbers. And this is our definition for the span of negative 1, 1, 0, and negative 1, 0, 1. So, because we can write V as the span of vectors, V is a subspace of R3.